Hello again. We would like to just continue our discussion of deflection in beams using the finite element method. I will just quickly review what we've done so far using the beam elements, and then the objective here is to go over a Matlab code so you'll be familiar with the writing code yourself if needed, and also utilization of this code will be useful in implementing design projects. So if you look here, let's kind of review back what we've done for beam elements. And I remind you that we have discovered that we can have a stiffness matrix, and the stiffness matrix is a 4x4 matrix for the beam elements, and then it has two nodes. Each node has 2 degrees of freedom, the deflection, and the angle of rotation. Therefore, given the length and the elastic modulus and the second moment of area, we can find the stiffness matrix. And then once we find the stiffness matrix for each element, then we assemble the stiffness matrices. So as we've done in this example, we have a stiffness matrix for each element. We have 3 elements, so we have 3 stiffness matrices, and then we assemble them in a big stiffness matrix, which is 8 by 8 by a shift along the diagonal, and the shift will have to be by the degrees of freedom, so we shift by 2. In the example that we did before for the spring elements, the shift was only by 1, so the K1, which is the last element of the stiffness matrix of element 1, was to be superimposed or added to the first corner element of matrix for stiffness element, the stiffness matrix for element 2. Here we have 2 degrees of freedom, so we have to go 2 down, and that gives us an 8 by 8 matrix, as you can see here. So we want to formulate that and solve it in Matlab. Here's a Matlab code written by Professor Salisbury in 2010, very useful, and we can use it, and have a copy of it on the website. So it starts with CLC and clear. These are 2 statements to clear the workspace and the command window, and then you input the data. The elastic modulus is the same for the beam, for the 2 parts of the beam, and then we input beam properties. So this is a beam prop is a matrix, and it's a 2 by 4 matrix. It's a 2 by 3 matrix, and it has 2 columns. Each column has a length of 3 nodes. So we have the length of each element is given here, 40 and 20 and 60, and then the second moment of area of each element. So this is 2 by 3, corresponds to the example we have here, is that we have actually 3 different elements. So this is 1, and this is 2, and this is 3. So the properties are right here, and therefore we can input these properties in the matrix form, where the first column is the length and the second column is the second moment of area. And next we create another matrix that is called node def, and it has the nodes and the deflections which need to be specified. So these are like boundary conditions. So node 1 has deflection of 0, node 4 has deflection of 0, and these are the two known points on the beam. We can also input known node slope, SLP, in a 2 by 1 matrix. So it has the node, it has two rows. Row 1 will be the node, row 2 would be the slope, and we have only node 1. We know the slope is equal to 0 on the end that is attached to the wall. Then next we apply the nodal forces, and the nodal forces are in an array for app, and the array is a two-dimensional array. It has the node and the force, and basically we have only one node where the force is applied, and the rest of the nodes do not have applied forces on them. Then next we add another array that has the moments that's applied, and basically we have one node 4 as the moment minus 50. And we can obtain the results after we finish all of the calculations. We're going to obtain the results of the calculations at 10 different points along the beam. So these are not necessarily at the nodal positions, but they could be in between. And then we start the calculations. This is finding the number of elements as the length of the beam property array, but only we select the first column. So all rows, first column, gives us the length of the array, which is the number of elements. And then obviously the nodes are the same as the number of elements plus 1. And the degrees of freedom is twice the number of nodes, because 1 is for deflection y and 1 for the slope, which is theta. Now we construct the stiffness matrix, and the stiffness matrix is to be constructed in a number of steps. So first we have the stiffness matrix. Try to get rid of this here. So first we do look at the stiffness matrix, and then we determine the stiffness matrix for the entire system as K. We're going to call it K. And first we initialize it to zeros, because a lot of the elements in this matrix will be 0. So when we say zeros of the n degrees of freedom, this will create a matrix. This is a statement in Matlab that creates a matrix that has an NDOF by NDOF. That's the number of degrees of freedom, so it's a square matrix, and it populates it all with zeros. So that initializes the big stiffness matrix. And now we create the total stiffness matrix by a process. Here's the 3 for loops. So there's a 1 for loop here on I, and 1 for loop on the J, and then 1 for loop on the K. So let's see how these will work. First, we get the length of each. So the I will loop over the number of elements. So we have 3 elements, so we can get a length and an elastic property EI for that. So the first part is for element, and each element has a K, and this K is a section K. So K sec is for that section or for this element, which is what we have derived before. And we have all of the components right here. EI over L cubed times, so this is a scalar product, so you don't have the dot operator. Dot operator, we use it when we have arrays for operations with arrays, but here is just a scalar operation. So we multiply EI over L cubed times, and then we have the stiffness of the local element. So now we have three of these stiffness matrices because we have three L's, and these are every time we loop over I, we get one of those. Now, after we loop over I, we want to shift. So we want to populate by shifting. So we locate element in a global matrix by multiplying. If we have I for element number 1 for each element, we have a local location value of 2 times I minus 1. And then we start populating with this value of LOC. So this LOC, for example, if I is equal to 1, then LOC will be equal to 1. And then we go into the JK loop. The J starts from 0 and the K starts from 0. So the big matrix will have 1 plus 0 here, and then 1 plus 0 here. So BK of 1, 1 will be the old value. This is old value, which is 0. Old value is initialized to be 0. And then you add the section element in location J plus 1 and K plus 1. So J plus 1 will be 1 and K plus 1 will be 1 because the four loops are starting at 0. And then when you go back, now the I is fixed on the outside at 1, and then you're looping inside. First you're going to loop on the K. So as you move on the K, then you're going to populate the elements in the columns side, and then once you finish the K, then you're going to loop on the J, and that will populate the elements on the row side, and that you will be, so you're grabbing basically the elements from the section stiffness matrix, adding them to the old values, which are zeros, and then populating them on that corner. And then you shift. So once you finish the J and the K, then you go back and you're going to you shift to the next element where I becomes 2. So LOC will be equal to, we have 4 minus 1 will be equal to 3. And then you have LOC plus J and LOC plus K. So you're shifting now by 3. So you're adding now the matrix as a shift matrix. So you have the smaller matrix here, and then you're shifting here, and then you're shifting here to formulate the bigger, the full stiffness matrix of the system. Next, we construct the load vector, and the load vector is zeros again, but only the first column of the zeros matrix, because zeros makes a matrix. Remember that zeros makes a matrix, but NDOF, if I leave it like this, then it makes it NDOF by NDOF. If I just make it zeros of NDOF comma 1, this is just, it initializes or grabs actually the first column of the zeros matrix and assigns it to F. And then you check that this is not empty. So there's an empty check here. And then you continue with it in the next page here to incorporate the nodal moments. So in this now we have the F vector has started initialized as zeros right here, and then you, for I equals 1 to the length of this, of 4 applied forces. Applied forces has F4 applied has all rows and first column, and for that you just transfer into the external forces in a vector here. And you do the same thing for the moments as well. Then you transfer them here, and therefore I have now populated the F vector that I wanted to use as the right hand side. Once I did that, then I need to incorporate the boundary conditions, and the boundary conditions are going to be deflections and the slopes. So for the deflections and the slopes, I'm going to let you now continue looking at this carefully, how you put in the boundary conditions, and we remember the deflections or the slopes, if they're specified, we have to transfer them to the right hand side to change the force vector in here. Same thing for the slopes, so there will be some change in the force vector that is set on the right hand side. And once we go through that, then we're ready to solve. So we solve first is initialize U to be a column vector, has NDOF values of a number of components in it or elements, and then this is the key equation that we use. The displacement is equal to K over F, and this immediately solves the linear system of equations, and we're pretty much done on the solution right now. So the rest of the program is post-processing, and post-processing here is shown so that we can calculate just basically find the distance x, and then find v and find m. All of these are initialized to zeros, and then we grab the properties from the section section properties, the length and the second moment of area, use it here, and then we just do the computations for the v and m at these nodes as desired. And finally, we have now the can calculate now, print basically the force and the moment at different points, desired points, and we can also print the column data as you can see in here, and finally we can calculate the slope and the deflection at increments along the elements. As you will be able to follow that here, and then we plot the data in subplots. So the data, we have a 4x1 subplot, so 4 subplots and 4x1, and this is the first subplot, this is the second, this is the third, this is the fourth, and the first one, it's an area diagram, so it shades inside. This is x versus v, and this is x versus m, and this is x versus slope, and this is x versus y. So these are the 4 plots that we have here in the results, and that's basically what we've seen here. So if we go back, these are the 4 plots that you've seen before, and the plots show you the displacements, and they showed us basically the solution in which we have the shear as a function of distance, the moment as a function of distance, the slope as a function of distance, and also the deflection as a function of distance. And with that, we have a complete understanding of that code. And if you just try to download it and test it, now you have an understanding. It would be nice if you could go through it a little bit more in detail. I tried to give you some hints in here, but it would be useful if you can go through it by yourself and try to satisfy yourself that you understand all of the steps in the program.